No, I will find them.
How's your throwback? Honestly, not that bad. George? Where'd you guys go?
She found a Facebook marketplace. I was selling the Imperial Starship.
This side.
Where Starship?
Oh, I don't
Small,
know.
like this big?
Maybe go.
You're lying.
Not the GPS, but like the semi-largest one. And then with a fighter for another 12. So on our way, we literally went to go pick it up and got a Imperial Starship.
Pretty cool.
Yeah, built and everything.
You don't like those?
Yeah, I feel like I would drop it just to rebuild it.
Yeah.
No, yeah, we're gonna dismantle. It just came because the guy was like wanting to get rid of his stuff.
Wait, you like Star Wars?
What?
You like Star Wars?
I like Lego.
You don't care for Star Wars?
I don't dislike or like it. I'm watching Andor right now. I think Andor is probably the best TV show that's out.
I do think Andor is probably their best Star Wars show.
Yeah, because it's not like Star Wars.
It's very, very wide.
Yeah.
Good though. It's a
Yeah.
good show.
If you like Star Wars, you should read Star Wars Ring Theory.
Because it's really low.
It's a scientific book.
No. It's like a 42-page website. Okay, Lucia, cash money? Okay, any questions before Lucia takes us through the last part of chapter 5? So it's gonna be a short read. How many people read it? It's 2 pages. What's wrong, guys?
3-hour drive.
4 hours.
What are we talking about?
Went to Santa Barbara this week. For
Uh-huh. And so you can't open up your computer and look at your book?
It was dead. I didn't know on the way back.
Who's bro?
I was driving.
I was driving. So you should have read it to him. Oh my God. Okay. You gotta read. You gotta read when it's not your week. You're missing a lot of stuff just by leaving it there on the table. Right? There's a lot of questions I get week in and week out. I'm like, yep, it's in the book. Yeah, you wrote that before. We're gonna spend this week, we're gonna talk about choosing integration methods. And then we're gonna do our final project in class because I need to see you guys starting it, right? Because I see a lot of people who haven't started it, don't even have an idea. So you can't pass the class without a final project. I would hope that the folks in this room will all pass the class. You need to have done all the homework. Okay. If you had ChatGPT do all your homework, it's really obvious to me because when you ask for help or when I ask you a question about it, you don't know how it works. Now that's different than when I ask you a question about homework you wrote 5 weeks ago. And you're like, I don't know what the fuck I wrote, right? Because guess where the comments look better?
It's like by ChatGPT.
Yeah, but it's by ChatGPT because you don't talk that way, right? I know how you all speak. So it's okay to use AI to help you write the code, but it's not okay to use AI as a substitute for your thinking. Okay? So especially when we're thinking about our final project, if we want to use it as a framework, fine. But you gotta, one, credit it, because I'm seeing it in homework where it's not credited. Hey, ChatGPT wrote this code for me, but here's where I adapted it from, right? That's how you're supposed to credit work. Even if, for example, your friend was sitting next to you, said, I borrowed this code from Emmanuel. Emmanuel wrote it, and I just stole it. But here's what I did, right? That's called collaboration, right? You don't get through life without working with your peers, okay? You just got to learn how to credit them and to say, hey, this was my idea from here onward. Before that, blame Emmanuel, right? No, don't say that. Just kidding. Does that make sense? Okay. And you have to understand what was done. So even if you get a piece of code, even if you get a piece of code from yourself from an earlier homework, Hey, I copied this from example 6.9. You still don't understand it from 6.9, that's still on you, right? Okay. So I've warned you about reading the book. I've warned you about turning in all the homework. I've warned you about the final project being done. I'm going to warn you about writing a final project presentation. So that is something that you'll need to do. And then you will need to understand everything that you've done. Okay. Questions, comments, concerns? Okay, so today Lucia is going to finish up the integration section, telling us just in 2 pages, why we want to use a certain integration method. And then I would like that we work together, finish up projects and homeworks, ask questions. Okay. Okay.
So for this, we're gonna be seeing kind of what integration method is easier for what kind of problem you have. Since kind of all of these are important, all of these work, but they all have kind of their faults. So we have the sorry, like, okay, so we have the Romberg and the Gaussian integration method, and this allows us to make more accurate estimations of integrations using fewer points, but this really only works with a smooth surface or kind of evenly spaced apart like intervals. And this is kind of really only when these kind of behave. And if your function isn't smooth or it has like, or it's like, has like bad math, you have to do a lot of math, these won't work as well. This is kind of like a very simple way of doing it. But yeah, and then, but when we have like the trapezoidal rule from section 5.1, it's important for when we need like a fast, easy answer for an integration. This uses equally spaced sample points, so we are able to use it in lab scenarios, since we try to take equal intervals in lab, so like equally spaced apart times and stuff like that. This rule is also good for poorly behaved functions, like a varying window of time where it's like not equally spaced, and like the integrations that contain singularities, or they have like noise and stuff like that. And the adaptive form of trapezoidal rule, it also gives you this, but you will have to use, or you will have to have like a little bit more time to use that one. And then for the Simpson, it also is easier to code like the trapezoidal rule. And we also use this for samples that are equally spaced apart and that are even, or yeah, this rule gives better accuracy than the trapezoidal rule with the same or fewer points that are given. But this relies on a higher approximation of the integrand, which will lead to problems if it's not smooth or if it's noisy. Okay, so its adaptive form provides results of guaranteed accuracy, but it can be it can be stable, but it's not very stable for like not fun integrands. And then the Romberg integration gives us accurate estimations. It allows you to stop the calculation once you've reached your desired accuracy. This will not work well for widely varying integrants, noisy integrants, or integrants with mathematically, I like this mathematically, oh my god, pathological behaviors, please. And the Gaussian guarantees to give the same advantages as the Romberg integration, potentially high estimates from all numbers of the same points, like, but it would be poor performance that it behaves badly with integrands and integration points are unequal if the integration points are unequally spaced.
For when it talks about the difference between like Simpson's rule and trapezoidal rule, like trapezoidal rule is better for noisy integrands. What's an example of an integrand or like a function where you integrate it that's noisy? Is it like a really jagged sine wave?
Gosh,
What does noisy mean? Yeah, but what is noise?
background.
What is noise? You guys are making the shape, but what is it?
Unnecessary.
Yeah.
Non-differentiable?
No. I'm just asking, like, what is noise? Something you don't want on a spectrum? Okay. Let's use some better words here, right? I would call them random fluctuations of my instrument around, right? So as I sample something, whether that's a spectrometer, whether that's a spectrograph, whether that is a particle detector. Let's say I'm counting the number of muons. Let's say normally I get 500 muons on average, but every second I may get 485 or 501 or 590, right? And there is some scatter through random stochastic processes, things that are happening stochastically, which means randomly. They're coming from a random distribution. So noise is a random object on top of our data. So let's say you have a sinusoid like you're talking about, okay? Then you have a source of noise on top of that, which is making smaller perturbations. Now the noise can be larger than the signal, in which case you can't see anything and it averages to nothing, right? Can you have noise in simulated data? How do you do it?
If you add random.
If you add noise, okay? So you can have data that you simulate so that it has, noisy data. And you can compare it to the noisy data that you take in the lab and see if they look as noisy, right? Okay. It's just random stuff. We'll talk about random stuff next Monday. Did that answer your question well?
I think so.
Okay. So when we think about noise, and think about these different data sets, right? Which of these is appropriate to use noisy data? Everyone but Lucia.
Say that again, I'm sorry.
Which of these techniques is usable for noisy data? Everyone but Lucia. Someone ideally who hasn't talked today. Lucia, is that correct?
Let me look at my notes. I would use the trapezoidal.
Or
Would also be Simpson's rule.
Yeah.
Yeah.
both of them are probably more appropriate. Why is that?
accurate. Awesome.
It's because like, from what I understand or comprehend, it's like Simpson's rule doesn't have like those equal spaces, like how the Romberg equation has, so that, I don't know how to put it in words.
Okay.
But because it doesn't take into account all the pieces of noise rather than a more of an average, but it averages it out. If it's minimal noise, if it's a lot of noise, it's still gonna be messed up either way in the rule, but because we're using the endpoints and we're going from here to here at certain discrete intervals, and we can it's not gonna be as accurate towards the noise as it doesn't affect it as much as it's being spaced out.
Okay, I'm not sure I would use all of those words exactly that way. I think you have part of the right idea. It's about sampling, right? Part of our integration is about how we represent the area under the curve based on where we sample it. So we talked about A and B and all of these little places in between. The silliest thing to do and the thing that we don't do in this class would be to take rectangles, right? That's like the dumbest approximation. And you just cut them down to size and you make them an average, right? Trapezoidal, of course, you take a slanted line between the two. That's smarter, just by a little bit, right? But the slanted line knows nothing about the function. It's an approximation to a curve. The Simpsons rule also, it's an approximation. It doesn't know the actual function, right? So it looks like some 3 points together, curves together. Gaussian requires you to actually know and understand the function in some detail, right? Because it uses things about the function itself. So therefore you start to run into problems, right? Romberg is a little bit better, right? But it's best applied to smooth functions that don't have singularities. If your noise, if it cuts out or if it does anything weird, then the way that you're cutting this together is going to include or not include that singularity and give you wildly different values and have a problem with convergence, right? So generally speaking, these first two are probably better. You know, this one says it's less suitable for poorly behaved integrants. So as you head from trapezoid, sort of the dumbest possible form, towards Gaussian, you are using information about the function itself. And so you sacrifice whether or not that can be truly random. Because we talked about at the beginning, you have your signal and you add on top of it randomness. And as randomness gets bigger, your signal starts to become less important, right? Relative to the two. So if you want to do something that uses the function, if you can't see the function because of the noise, then it's not as appropriate, right? Are you happy? Okay. Anything else you want to say? Any other questions we have? Yeah.
It's not enough chapters we're gonna work on today.
Yeah.
What are we?
What did I say we're working on, folks?
Project.
Homework and project. Yeah.
Does that count for, can I, like, can we use this time, because sometimes we pair program and we don't have it? So we
Yeah.
hunt them down and be like, hey, can you share this with me, please?
Yeah, absolutely. Particularly if you might need it, right? Be like, oh shit, I did this really great image with Angeli on Thursday, and I really need that because I want to copy and paste it for my project, right? Just go over to their workstation, track it down, or have them email it to you. Okay. So yeah, so today there's nothing assigned for pair programming. There's not even a homework assigned. So I'm debating whether or not to have a homework assigned or whether or not to do something like this. Oops. Do something like this for random numbers. And using what we have learned. David's not here. Trinity's not here. Do we want a homework that's due the last week of class? Come on. Yeah, I mean, you guys just have to do them. I'll grade them when they're done. People don't turn anything in. There's nothing to grade. Yeah, I mean, that's the question, right? So if there's no homework, I'll expect a higher level of project.
How high? How much higher?
A homework higher. Instead of 1.5 homeworks, 2.5 homeworks. The total amount of work that is done in this class should be constant, right? We don't just get to take time off because, well, it doesn't really feel that much like a class. Yeah.
What would the homework consist of? Like what time?
Chapter 10, random numbers. Sounds fun, right? I feel like we should do it. And we'll take this week, we'll do this one here and this one here. And we'll say homework 9 is due on the 12th. How's that? We like it? Don't be mad. Get glad. Yeah. All homework is due the 5th except for homework 9. Same as before. Yeah, everything that you wanted to turn in must be turned in on the 5th. Yeah, because you need a whole week to turn in the final, right? So I then expect you to turn in the code on Monday, and I believe that our final presentations will be the 15th, which would be in class on Wednesday.
So you're saying my final code should be due or be done on Monday, the 5th?
Yeah.
Holy shit.
That's what I've been yelling at you for. I've been screaming the whole semester that the semester is almost over. And everyone's like, not really, though. This other class is more frustrating.
I personally understood code submitted by like the 12th. I personally understood.
Yeah, okay, you're good. You turned it in? Oh,
I'm
well, you're
working on
going
it.
to, but you have it planned for the 12th.
That's my intention.
Okay.
To turn in.
Yeah, it says right there the 12th.
But I have my progress already.
What?
Says code submitted the 12th.
Yeah, code for your code proposal due, code submitted.
Yeah, the 12th.
Yeah.
You're saying Monday the 5th.
No, Monday the 5th is what? All homework, which
Well,
is in the syllabus. Except for chapter 9.
My question was, my final code submitted on the 5th.
Oh, no, sorry. The final code should be submitted on the 12th.
Okay.
Yeah,
Okay,
what did...
cool.
You said.
You said the
You
5th.
said the 5th.
That's what I was like.
No, all the homework is due on the 5th.
You said that.
You got 7 days to get my shit together.
Yeah. Well, you do have 7 days to get your shit together. Right? Because all your shit needs to be in a bag by this day. All your homework, right? Except for 9. Which now it doesn't really feel like all the homework. Homeworks 0 through 8 need to be in a bag by next week. And that way I can look at them and yell at you. Okay? Yeah. Yeah.
What days are you gonna be here this week?
Well, I'm moving on Thursday, so I won't have office hours tomorrow or Thursday unless someone wants to be there. I'll be here on Wednesday, and I might be here for part of Friday if people want to do Friday session, cram session. It's very helpful to ask questions, because then you will know what you're doing. I think when you are butting up against not having enough time, one of your biggest enemies will be spinning your wheels, like not knowing how to get started or going down the wrong path, doing something wrong for about 15 minutes and looking back and seeing, oh, I should have just changed this one line. So this is where when it's very useful to ask questions sooner rather than later to make sure that you don't go down a path that has no end. Or if you're running into a problem and you keep getting the same error or something similar, send me a message quickly, right? Because time is of the essence.
So,
C'est bon?
where you're moving to.
It's a house. It's moving from one house to another.
So, no.
My landlord sucks, so. Okay, comments, questions, concerns? And then freaking out?